So we're switching from the second derivative to the Laplacian. Musically speaking, we're switching from a string to a drum. A drum, are there funny shaped drums? How about a shape like this? Can a drum be this shape? Yeah, it's a shape that's very dear to my heart. And of course, a drum could be this shape. And when you strike it, it changes its shape a little bit. That creates a restoring force, and so it begins to vibrate. And that's the source of the sound. What do you think the equation looks in this case? We could kind of do similar analysis. But if we think about the drum and think about what matters, well, interesting question. What matters? Okay, here's what matters. Does the position of the drum matter? It does not. Clearly, I have nothing else to say about that. Does the orientation matter? Maybe a little bit because of the acoustics, but not really. Right? So the only time you get a restoring force is if you change the shape. So you have to get to the second derivatives. And here u is a function of time, but also x and y. Because now it's not just a linear thing, it's a two-dimensional shape. And the equation will be, once again, density times acceleration equals stiffness times what? What combination of second derivatives? It has something to do with second derivatives. Yes. So it's usually denoted by this symbol. It's such an important combination that it's worthy of a symbol, u, and it's called the Laplacian of u. And I have a lot to say about the Laplacian, and maybe now is not the right time to do it. But here's the definition of the Laplacian. It's exactly what Jesse said. It's the sum of second derivatives. And I will change the notation a little bit. I will say for the derivative u sub x, x. That means second derivative with respect to x. And of course, we'll also use u sub y, y, and u sub t, t. There are just so many partial derivatives that it becomes quicker to write. So it's the Laplacian is this plus, and I just want to say, I can't resist saying this, because it's in some way my field of study, or at least the machinery that I use called tensor calculus. So I'm not going to talk about tensor calculus right now. What I should say as a teaser for that amazing subject is that this should fill you with suspicion. An expression like this should fill you with suspicion. And the suspicion is that you look at this drum, and does the drum, rhetorical question, know anything about the x and y coordinates? Did it meet Descartes? What does it care about Cartesian coordinates? It knows nothing about the Cartesian coordinates. Why is it that if you choose Cartesian coordinates, that it's this very nice expression? Well, what would happen if you chose different Cartesian coordinates? Rotated them, or stretched them. You would no longer call them Cartesian, but still you would call it a square grid. Would it still be the same expression? It's too nice of an expression. It's too arbitrary. Nice is not even the right word. Yes, it's very nice. I admire it myself. But you can actually think about it very easily and realize it can't be this. Because if you switched your coordinates from centimeters to inches, you would realize that there needs to be a coefficient, because all of the derivatives will change by a factor of 2 point whatever squared, because there are two derivatives. And so you would need an adjustment out in front. Well, where is it? You might say, well, we're mathematicians. We skip coefficients like 1/4 because they're not material. Okay, but what if you switch to polar coordinates? The drum doesn't care. The drum just is. It doesn't know what coordinates you imagine on it. What would this become? U, the second derivative with respect to r, plus the second derivative with respect to theta. It can't be that because the units don't work out. So it's just way too arbitrary to buy into it. As a physicist, you should say that's just way too random. You chose it because it's nice. This is not meaningful. At least that's what you should be telling yourself. An expression like this cannot be meaningful because it doesn't describe the drum or its shape. It describes, yes, there's a little bit of what the drum contributes U, but it's the coordinate system that contributes the bulk of that expression. And if you change the coordinate system, this expression would change completely. So it's very confusing, and I would say suspicious to the point of dubious. So if you want to have complete clarity on this question, you have to study tensor calculus. But since we're continuing with our ode to the second derivative and now to the Laplacian, let me actually reverse my statements and tell you that this actually does have meaning. Yes, the scaling argument that I used is still valid. There might have to be some factor here depending on what units you choose. But if you do have Cartesian coordinates and you do evaluate this expression, it has a certain very, very important meaning. So we'll do a calculation and I'll show you what that meaning is. So what you basically need to do is to be able to say what this expression represents in a way that doesn't include coordinates. You just have to say, it's this. It's this geometrically. So let me tell you what it is, what the Laplacian measures, and then we'll derive it. Okay? The Laplacian measures the degree by which the value at a point is different from its neighbors, from the average of its neighbors. That's how I want to put it. So it's the degree by which the value at a particular point varies from the average of its neighbors. So if we imagine that u is just a linear function, in other words, represents a plane, can you see that the value at any point is exactly the average of its neighbors? And by its neighbors, I invite you to think of a circle. So here's the point centered, and then there's the circle centered at the point. So some points are lower, some are higher, some are the same height. But on average, these values equal exactly the value at the center. So if u is a linear function and therefore represents a plane, then its Laplacian, by this argument, will be 0. And of course you know that it's 0 because if it's a linear function, both of these derivatives vanish. But if it's not, if it has some shape, let me show you the calculation which gives you the geometric interpretation of the Laplacian. Okay, so here's what I'm going to do. I'm going to say, let's look at this point. This point let's actually put the origin right there. So let's call this point 0, 0. In u at this point. U is a function of x and y. Right now we don't have time. We're just doing it at a particular moment of time where we have a certain shape. So this is the domain of the definition, and u lives in the z-axis. So if you want to imagine its graph, it'll be something like this. So all of the pictures that I'm drawing are in the domain. So we're comparing u at this point. We draw a little circle around u. Let's erase this. Here's a little circle around u of radius r. Let's pretend that it's small. And what we're going to do is we'll find the average of all the values of the function u here on the circle and compare it to this value right here. And we'll discover that that discrepancy is proportional to the Laplacian. And that will give us some comfort in this rather arbitrary expression. So here we go. Here's the average value of u. Average of u over the circle. I don't want to there are mathematical symbols that represent this, but average of u over the circle. Now that looks like I'm dividing by 0. I'm just trying to use common language. Well, I have to add all of the values together. So I have to basically integrate u over this circle and divide it by the perimeter. That's what I'm going to do. So it's going to be 1 over 2 pi r, because that's the perimeter, of the integral over the circle, that's my notation, over the circle of u ds. Okay. But it's a small circle. So we're going to approximate u. So we'll look at the value here at the point x, y. Small x, small y, distance r away from the origin. Here, u will be equal, u of xy will be equal, we'll write a little bit of a Taylor series for it. Who remembers Taylor series from multivariable calculus and what they look like? So now I have to plug it in here. That's what u is. U of 0. Can I denote it by u sub 0? Times x. And this will be a line integral. So just to save space and time, now is the time to parameterize this circle. And to say that x equals r cosine alpha and y equals r sine alpha. And ds equals r d alpha. Because that's, again, I'm skipping the calculus details. We could go through the formal procedure of taking this invariant integral and parameterizing it and converting it into an arithmetic integral like you did in multivariable calculus. But we'll just agree that ds is r times d alpha. So u sub x times r cosine alpha very simple integrals. This is the integral of u0 from 0 to 2. Where's my r squared? No. Yeah, so excuse me. u0, let's not forget this factor of r, from 0 to 2 pi. Well, that's just 2 pi r u0. And because we're dividing by 2 pi r, we're just left with u0. Okay, what about this integral? Cosine alpha from 0 to 2 pi. Well, that's the indefinite integral. What about 0? Of course it's 0, because cosine has a complete period. So that's 0. That's 0. Not surprising that the linear part disappears, because that's exactly what the plane part is. Bottom cancels the top. So of course the average there zeroes out. Okay, the same thing will happen here, because you're looking at 2 cosine alpha sine alpha, which is the same as sine 2 alpha. Also has 2 complete periods between 0 and 2 pi. So this part is gone also. So we're only left with this and this. Does anybody remember what the integral of cosine squared alpha is? And in parentheses, we have u sub, you're right, pi r cubed, u sub xx is the Laplacian. Okay? But let's simplify just a a little bit more, so equals u sub 0 is that the difference between the average of u and the value at the center. So if you surround a point with a circle and you find the average of those values and you find the discrepancy from the value at the center, it is proportional, and that proportionality coefficient is r squared over 4 to the Laplacian of u. And of course there needs to be a multiple of r squared, because if you think about units, whatever u represents, if it's temperature and is measured in Kelvin, when you take its derivative with respect to x once, it'll pick up over meter, and when you do it twice, it'll pick up over meter squared. So if you want your units to match, there needs to be something that's proportional to r squared. And it also means that as the circle shrinks, that discrepancy gets smaller and smaller. And that discrepancy is proportional to r squared. So of course that's the case. But what's very interesting is that it's also proportional to the Laplacian. And that's very important, because now you can, you see that the statement that I made earlier is correct, that the Laplacian represents, even though you have to deal with this 4 and this r squared properly, but it represents the discrepancy between the value at a particular point and the average of its neighbors. And doesn't that describe the change in shape? Because if you turn something without changing its shape, then you don't create a discrepancy between the value at a point and the value at its neighbors. It's only when you do this that the value at a point and the average of the neighbors changes. That's it. I don't need to make another drawing. Right. So this gives us much greater comfort that this seemingly arbitrary combination of derivatives is actually meaningful. Actually, I do want to draw a picture. So going back to this drum, the interpretation is that if I pick a point and draw a little circle and find the average of the values of the function on the circle, and I compare it with the value at this point, the discrepancy will be proportional to the Laplacian. So why was it important to draw the drawing? It was because the statement that I just made has absolutely nothing with the coordinate system, right? The statement, I set value here, no coordinates. Draw a circle, don't need coordinates. Add them all together and divide by the length, no coordinates. Find the difference between the two, no coordinates. Completely coordinate-free formulation. In fact, you can define the Laplacian this way. Pick a point, draw a circle, add them all together, divide by 2 pi r, and then on top of it, divide by r squared over 4. Take the limit as the circle shrinks. That's the Laplacian. No mention of coordinates whatsoever. And it just so happens that you will also get a value that equals this combination of derivatives, which means that this combination of derivatives is meaningful. And it's one of the reasons why the second derivative is my favorite. Just so many things you can do with it and end up with meaningful quantities with a physical interpretation. So that completes my ode to the second derivative, and I'll answer your question. Yeah, 2, 3, and then of course beyond that you don't have a geometric interpretation, but the analysis still works, absolutely. Yes. The question that remains open, and you will answer in your homework, is what if you chose a different coordinate system, which we will absolutely have to do for the problem that we'll consider in the next lecture. If your drum was a perfect circle, an interesting question, you would want to use polar coordinates because that matches the geometry of your problem. So what does the Laplacian look like in polar coordinates? It's certainly not the second derivative with respect to r plus the second derivative with respect to theta. The units don't even work. So it'll be a different expression. So this expression is only valid for Cartesian coordinates. If you want to get the same quantity, a concept with the same interpretation in a different coordinate system, the expression will have to be different. And we'll get there.